Both commercial and residential photovoltaic, or PV, installations, commonly called solar panels, have become more widely used in the last 40 years, and now utilities are starting to see, and in some cases own and operate, battery storage systems to both extend the use of solar energy into early evening hours, and also to help flatten the now notorious duck curve, which represents a timing mismatch between peak renewable generation and peak demand. Electric vehicles, or EVs, have also become more popular in that same period of time. Let's take a closer look. The traditional meter measures the energy delivered via the grid to the site, watts delivered. Modern meters are also capable of measuring energy delivered from the site back to the grid, watts received. Because it measures the net of these, or watts delivered minus watts received, this scheme is often called net metering and has been around for about the last 40 years. The distribution panel is usually connected immediately after the meter and is responsible for distributing energy to sub-circuits within the home or business, and typically contains circuit breakers to protect and control each individual sub-circuit. Now let's look at newer equipment beyond the traditional installation. The solar inverter converts the DC from the solar panels to AC for both local use and to deliver any excess energy back into the grid. The battery provides local energy storage and also converts DC from the battery to AC for local use. Unlike the solar inverter, however, it must also be able to send energy the other way to recharge the battery. The transfer switch helps to coordinate all of this, allowing the solar panels to charge the battery, or the battery to supply energy, or some combination of those. Let's look at a summer weekday's worth of power flows for an installation like this. In the early dark hours before dawn, the electric vehicle has already fully charged overnight, and the people in the house are still asleep. Energy use is very low right now, and all of it is being supplied by the grid. Because this home is on a time of use, or TOU, billing plan, the price per kilowatt hour varies from the off-peak time right now, when the rate is lowest, to the peak price when the rate is highest. Here, as in many places, there are also intermediate shoulder rates between those two. A few hours later, the people are getting ready for work and school. Lights are on, breakfast is being cooked, and perhaps the automatic thermostat has adjusted the temperature to a comfortable level. By midday, the sun is shining brightly, and so the solar panels are producing more energy than is needed at the moment, so that excess energy is used to charge the batteries. That afternoon, a tree falls somewhere in the distribution lines feeding this home, and so grid power is temporarily out while utility crews are dispatched to find and repair the fault. For now, the power supplied by the PV and battery are sufficient to continue to run critical loads, perhaps refrigerator and air conditioning. Later that day, the people have returned and are doing homework, watching television, and preparing dinner. Energy consumption has risen and solar output fallen, but because this is a peak rate, the system is programmed to prefer to draw energy from the battery rather than the grid at this time. In the evening after sundown, during a shoulder rate period, solar panel output is dropped to zero, and the battery is discharged to the point it's also no longer delivering energy. All energy is being supplied via the grid. After the people have gone to bed and demand across the system is low, the electric vehicle has been programmed to charge while the rate for power from the grid is least expensive. It is programmed to complete charging in the early pre-dawn hours, ready for another day. One way for utilities to gain insight into these power flows is to measure them by installing additional AC meters of the same type already employed by the utility. This has the advantage that utility personnel are already familiar with the meter, that because it's of the same type, it can use existing AMI communication paths to convey its data, and that existing head-end software should be able to read and interpret the data. However, while these power flows may have inverters, they're inherently DC devices. For that reason, several utilities have asked EPRI to investigate the use of DC metering for such applications. There are currently DC meters available today, but they're typically not designed for communications with AMI systems, and their measurement and reporting is different from the standardized meters used by utilities today. To address this need, both ANSI and the IEC are working on creating standards for the measurement of DC. Also, the U.S.-based National Electrical Manufacturers Association, or NEMA, is working on a DC submetering standard. EPRI has launched a supplemental research activity to identify the requirements for DC metering and to work with standards development organizations such as the IEC and ANSI to further the standardization effort, which could include both measurement and data communication standards. If that sounds like it might be of interest to you, please contact us. We look forward to hearing from you.